Okay, so now the question becomes, if we're given a set of vectors, how do we determine whether that set is linearly independent? So here, let's say my set was the set defined by the vectors 3, 4, 5, 2, 9, 2, and 4, 18, 4. Okay, and again, in the last video, we ended on the theorem that stated that this came down to solving a linear system, a homogeneous linear system, where the columns of my matrix were made up of these vectors. So we had 3, 4, 5, 2, 9, 2, 4, 18, 4. All right, and since we are dealing with the homogeneous system, I just avoid putting that the augmented part, since it's just all zeros here. So I just work with this with this matrix here, and I reduce row echelon form, so I perform my row operations, and I come down to this matrix here: 1, 0, 0, 0, 1, 2, 0, 0, 0. All right, so we have a matrix with 2 pivot columns. All right, and as we can see here, right, we have three variables, right, which correspond now to our alpha 1, alpha 2, alpha 3. Right, so it's a consistent system, right? We knew that from the start, that it was definitely going to be consistent because it is a homogeneous system, right? But here we have that it is going to be not linearly independent because it consists of more than just a trivial solution, right? And again, that's how I just want to interpret that, right? What I have here, I've arrived at a conclusion here where I have a consistent system with infinite solutions. So what does that mean for my vector set? All right, so what I can state is that this set of vectors is linearly dependent because there exists a non-trivial solution to the linear combinations. All right, and again, just to illustrate here, what we're saying here is that given this set, set it equal to the 0 vector, then I can find non-zero values for alpha 1, alpha 2, and alpha 3. Now, one of them may be 0, right? It's just depending on what the linear combination is here, but not all of them are going to be. All right, and we can see clearly here, this one, vectors 2 and 3 here, right? It's double. That third vector is double the previous one. So yes, it makes sense that that showed up in our solution, having a linearly dependent set. All right, let's do one other example here. So let's say we have a set S here, which we define by the vectors 2, 3, 1, 0. Set 0, negative 1, 0, negative 2, and 0, 0, 0, 1. Okay. And again, I want to determine if it is linearly independent. So I start off setting up my matrix where the columns are the vectors. All right. And then I reduce row echelon form. And we get the matrix here. Where we have the trivial solution, right? Alpha 1, alpha 2, alpha 3, right? And what it's telling me is that here I do have a linearly independent set, right? Since only the trivial solution exists, right? So what this is telling me is that here, all right, given this linear combination, right, this linear dependence relation, that the only solution here, right, that we just shown here with our reduced row echelon matrix, the only solution for this is the trivial solution. All right, now here, if we are relating here the number of pivot columns with the number of vectors that we have, right, we can see here that there is an interplay happening here that is going to determine whether a system is linearly independent or not. Right, and that's going to bring us to here in our textbook here. Let me switch over here. Theorem LIVRN. That's linearly independent vectors R and N, right? And again, R is the number of pivot columns and N is our number of vectors. Suppose that we have that S is this set of N vectors, subset of Cn, and A is the M by N matrix whose columns are the vectors in S. All right, so it's just what we've been doing now, right, as solving this homogeneous system. Let B be a matrix in reduced row echelon form that is row equivalent to A, and let R denote the number of pivot columns in B. Then S is linearly independent if and only if, right? There's that word, right? That strong connection, right? If and only if N is equal to R. Okay. So, toggling back here to my examples. Okay, so we saw here in our first example, right? We had three vectors, right? So N was 3, and here R was 2. And we saw that those were not the case, so by definition, right, if and only if, right, not linearly independent. In our second example here, we have N to be 3, and we have 3 pivot columns. So R is 3. And then that led us the result that it was linearly independent. All right, so all that theorem is telling me is that the number of pivot columns should be the exact same as the number of vectors. Now, as you can see, there are some limitations here then as to how large a size of set of vectors I can have that are linearly independent. All right, so if we think of, all right, we have row, right, this matrix filled with entries, right, all along the rows and columns and stuff, right? So here, if I have n vectors and I'm in the Euclidean M space, M rows, right, then there is a limit into how many vectors I can have that are linearly independent in a set. Right, so here, if n is bigger than m, right, then that set I can automatically conclude is going to be linearly independent. Excuse me, linearly dependent, because there is no way I can have n number of pivot columns if n is bigger than or m, right? Because the number of pivot columns, again, is limited by the number of rows, right? So at most I can have m pivot columns. All right, so that is a result that, keep in mind here, that kind of flows from just this idea of our homogeneous system, and it's stated in our theorem here. So let me over here back to our textbook here. So theorem MBSLD. More vectors than size implies linear dependence. Suppose that S equals to U1 through UN, subset of C sub n, and n greater than or equal to n. Then S is a linearly dependent set. All right, so again, what this is stating here is that if you have more vectors, right, that you do have rows in the space, right, and the size of the space that you're dealing with, then it's going to be linearly dependent. All right, so here, let's say we're asked to find whether let's say you were given this set of vectors and you were asked, is this set of vectors linearly independent or linearly dependent, and why, right? Give reasons for your conclusion. Well, I can conclude from the previous theorem this is going to be linearly dependent without having to do any calculations, right? Because of those last two theorems here, right? And we just simply state there are more vectors than there is row in each one of our vectors here, right? So here, if we try to put this in reduced row echelon form, you can have at most, and this one will have two pivot columns, right? But I have four vectors, right? In order for it to be linearly independent, it should have four pivot columns. But we see here, this is going to be impossible, right? In this case, n is bigger than m. So by that theorem, it must be linearly dependent. Okay, so, and now the bigger question answered here is that, well, every set, the largest set in R2 space consists of exactly two vectors, right? That's the largest linearly independent set, right? It's not unique. We can choose these vectors in many different forms, but it cannot hold more than two. All right, if it has more than two in our R2 space, right away